Anyway, welcome to all. Today, I'll be handling the concept of heat and mass transfer. You know that it is actually a part of our second unit of industrial microbiology. Heat and mass transfer uh, is applied in various fields, even in engineering, chemical engineering, wherever as it process out there. These heat and mass transfer concepts were important. In fermentation technology also, it's of so much importance that it is studied at the bioprocess level or chemical engineering level. Now, my intention is to just give you a brief account of what is heat and mass transfer and how it is applied in case of a bioprocess. So let me share the presentation with you. Uh, so when there is a temperature difference in a system, heat flows from the region of high concentration to the region of low concentration. So if there is a concentration difference or there is a temperature difference, you know that there is a flow of solutes or even heat from the region of high concentration to the region of low concentration. So body under consideration or the system under consideration may be solid, liquid or gaseous. In any forms of state of matter, we can see this type of movement or this type of flow of temperature from a region of high concentration to a region of low concentration. So that's actually that's a heat transfer. So in thermodynamics, normally when we have a system in a certain state and that system undergoes certain heat and work interactions. Because of this heat and work interaction, the system goes from one equilibrium state to another equilibrium state. And during that shift, it attains a certain state which is described by its another set of temperature, pressure, etc. So that means if there is a system, say a vessel containing water, you can heat it. So that it is normally that system, that bowl with the water will have its own temperature, pressure, and all these parameters are there. So when heat or work such interactions, if you pressurize that in a pressure cooker or if you heat it in a heater, so heat and work interactions when you are applying to such a system, it will attain another state of maybe it will boil or it will reach another high temperature state, and maybe there is a if it is a within say an autoclave or a pressure cooker, then it will have another temperature and pressure and different other conditions are there. So as a result of applying heat and different forms of work, this system or a system will move to another state, and that can be described with for example, after heating, normally the water which is at say 25 or 30 degrees Celsius in an autoclave. After heating in the autoclave, it may reach 110 degrees Celsius with 110 lb pressure or something. So that difference is made by interaction with the heat under different forms of work. So in thermodynamics, we never consider the time or rate factor in the process. Okay, the water from 30 degrees Celsius is now raised to 110 degrees Celsius or 120 degrees Celsius. So that is considered, but the rate of transfer of this heat transfer, rate in which the temperature of the water is actually it is raised to the higher temperature of 120. That rate of transfer is normally addressed in case of thermodynamics. But in heat transfer, what is the rate at which this heat flow occurring? How much time it will take to attain that state? That is more important. So in normal thermodynamics, that time factor or the rate factor is not a concern. But usually in such industrial processes or wherever heat transfer occurs, this time factor is more important. At what rate this heat exchange is occurring. So that is more important in such industrial process. So in heat transfer, we are considering that factor also. So the distinction between thermodynamics and heat transfer is the incorporation of a time and rate factor in heat transfer. The subject dealing with the rate at which a heat flow occurs is called heat transfer. So that can be attributed as a definition for a heat transfer. So it's a subject that is dealing with the rate at which the heat flow occurs. So why it is so important? Once we have the laws which govern the process of heat transfer, we will be able to, or we will be in a position to design equipment and shape the size and shape of the equipment can be designed in which heat transfer occurs. For example, if you want to design a radiator, or if you want to design a fermenter or a cooling system, cooling jacket of a fermenter, then certainly you require such a type of understanding on the heat transfer process, so that an efficient system or an equipment with a cooling equipment or a heating equipment, such type of equipments can be designed. The size and shape of the equipment can be designed only if you understand the principles of heat transfer. Now, take the example of a car radiator. It receives hot water coming from the engine cylinder valves. So the car radiator is connected with the engine valves. So the hot water from the engine valves is now taken back into the radiator and radiator valve. From the cylinder valves, the water is taken to the radiator. Typically, at that temperature, that hot water that is coming from the engine will be about 395 degrees Celsius. And it is cooled by air that flows over the radiator. So the radiator is having a specific design through which the air passes. So through the fins of this or through that net of this mesh of this radiator, when the vehicle moves at a higher speed, that airflow will have a high increased velocity. So that will flow through that radiator, and in that air that is tracking the front end of this radiator, that air actually it is transferring that temperature, or the heat transfer is occurring between the air that is flowing through the radiator and the hot water that is circulating through the radiator. Okay, the hot water is normally at 395 degrees Celsius, which will be bring down to about, for example, 5 to 10 degrees Celsius will be brought down by this air. So it is not taking to a very low temperature, but some amount of cooling is provided by the airflow. And it's cooled by the air that flows over the radiator by 5 or 10 degrees Celsius, and it is again circulated back. It will be circulated back to the engines, and this process of circulation of this coolant, it's not water. Nowadays we are using coolant, that will be circulated back into the engine, and then almost the coolant at 395 degrees Celsius will be again taken back to the radiator. And again the airflow, it will cool it by 5 to 10 degrees Celsius. So that is, hot water picks up the heat in the cylinder or cylinder walls and gives up to the air in the radiator. So that's what happens. So from the hot engine, the water or the coolant takes up it transfers. The engine walls transfers that heat into the coolant. Then the coolant transfers into the air that is flowing through that radiator. And this device, that's a car radiator, is a heat exchanger. To design that radiator, you need to understand the convective process of heat transfer occurring on the air side, on the water side, and the conduction process occurring in the fins and tubes. So all these things needs to be understood, and it should be properly understood, and so that you can design a proper or a good quality radiator for a car. So in that case, you require to understand the convective and conductive process, etc. We will look into that one. So there is another term. Actually, we are addressing heat transfer and mass transfer. The mass transfer is when there is a concentration difference or a movement from a region of high concentration to a low concentration of substrates or molecules occur, then that is a mass transfer. That's again from a region of high concentration to a region of low concentration. Example, in a room in a room, the air has about 4:1 ratio of nitrogen and oxygen. So let us release some amount of compressed nitrogen at one corner of the room. So from the corner of the room where we have just released a high concentration of nitrogen, compressed nitrogen, it will diffuse throughout the room and distributed uniformly throughout the room within within a fraction of minutes or something. Now, diffusion occurs until it reaches equilibrium. So the equilibrium, when the equilibrium will be attained, because when the uniform additionally released to nitrogen is uniformly distributed throughout the room, and now maybe you will have another ratio of 3:1. Sorry, 4:2 or 2:1, something like that. So if you release high quantity high quantity of nitrogen into the room, then you will have another ratio other than 4:1. And that will be uniformly distributed and it reaches an equilibrium. So the mass transfer occurs when there is a concentration difference. And if there is a concentration difference, it will be distributed through various means like convection, etc. in case of heat. And in case of mass transfer, we have diffusion process which diffuses the molecules throughout the room. And finally, we will have another state of equilibrium other than this 4:1 ratio. So that's what happens in case of a mass transfer. Now, some problems of interest in the heat transfer. So, heat loss through thermal insulation on a stream pipe. So, you can just look into some of the examples where heat transfer occurs. So usually you can see that there is a heat loss through a thermal insulation on a steam pipe. So if you are taking steam through a pipe, there are many restaurants who are working on steam-based cooking, where hot steam is used for cooking. So that will be brought to the concerned target site through hot pipes. And steam is also used for sterilizing the entire equipment like large fermented bioreactors, etc. Okay, so that requires steam to be carried through pipes, steam pipes. And these may be insulated thermally so that it prevents the loss of heat. And if the thermal insulation is not proper, then these heat loss will be significant. Now, the heat transfer to water flowing through a tube. If water is flowing through a tube, then heat transfer can occur, for example, in a coolant system that is working in a fermenter. Maybe there are cooling pipes through which cold water flows, and the heat on the surroundings will be transferred to the cold water. And that is an example of even the, say, the condenser of your distillation unit itself is an example where condensation process occurs through cold water that's running through the pipes. So there, the process occurring is a heat transfer to the water flowing through a tube, where the cooling tube is there, and the surroundings of the air or steam will be on the outside, from which the or even fermentation medium will be on the outside, from which the temperature will be transferred to the cold water running through the pipe. Now there are heat transfer in an electric furnace. There is another case. So I am citing these examples, and we can see the representation, diagrammatic representation here. Here you can see there is a pipe in which steam at a high pressure or a high temperature is running through this pipe, and this is the interior of the pipe, and this is the walls of the pipe, and this portion is the insulator. So the quality of the insulation and thickness of the insulation is important while you are designing such a pipe for transferring the steam. Here, this graph shows that with the increase in the insulation, there is a reduction in the heat loss. So if there is a more thickness for the insulation, then heat loss will be minimum. if you have a very uh, small thickness or very light thickness, coating for this pipe, then that means heat loss will be maximum. So this graph exactly describes how heat loss and the concerned insulation is related. So if you, and you have to decide to up to what extent you want. For example, if you want to transfer this steam to 10 meters or 100 meters, so and so. So with the increase in the length of the pipe, there's a more possibility of heat dissipation and heat loss. So in that case, if you want to take this steam to a very long target or a distant target site, then certainly you may require a higher insulation so that heat dissipation or heat loss will be minimized. And in that case, you have to choose a pipe or design a pipe with a thicker insulation. Whereas if your target is a nearby site, so you don't have only a few meters, then the possibility of loss of steam through heat loss of the steam may be minimal because the distance is not so much. In that case, you don't require a pipe with a higher insulation. So to decide what type of pipe that you require and what is the quality of the insulation that is required for the pipe, you need to understand the principles of this heat transfer and heat loss. Especially that type of pipes are used for transferring, for example, steam that can be used for steam sterilization, etc. of the reactors. One of the practical applications of such a heat exchange in a bioprocess. Now this is another picture that shows heat transfer flowing through through water in the tube. So this is the tube. This is the tube, and water at 30 degrees Celsius is flowing through this tube. So this dotted line represents the water that is flowing in this direction, and the thickness of the tube is about 2.5 centimeters, through which the water at 30 degrees Celsius flows. Now, on the other side, on the outside of this tube, there is a condensing steam or a steam at 50 degrees Celsius or higher temperature. Steam is present on the other side, or maybe it's a medium that you want to cool down. So anything where you actually, this is a concept of a cooling system or a condenser. So if you want to cool a medium using a cooling pipe through which the water flows, then the hot water, the temperature of the steam or the medium or fermentation medium which is present on the outside of this pipe will be transferred. The heat will be transferred to this through this pipe walls to the water flowing through this one. And this shows the relation of this length of the pipe. So it's a 2.5 centimeter thickness pipe with 2 meter long. And here we have the 30 degrees Celsius. And when we move to this side, the temperature actually increases because heat transfer occurs and the temperature of the water will be higher when it reaches this point because of the heat transfer. And if you say an example, for example, you have instead of 2 meter pipe, you have 4 meter pipe. Then again the graph will go up and it will reach a further higher temperature because with the increase in the length of the pipe, more heat transfer will occur and maybe it will reach another higher temperature other than that transfer occurring during the transfer through a 2 meter pipe will be less than that of the heat transfer that is occurring in a 4 meter pipe because that much length is there. By the time it reaches the other side, more heat transfer will occur. Okay. Now, this is another example in which a heat transfer of a furnace, where these are the electric heaters in the furnace, and heat will be transferred from this furnace through the air into the steel strip that is actually is moving through this roller. So, in the furnace, we are heating this steel strip using the heaters which is set there. So in this case, actually, the heat from the heaters is transferred through air to this metal strip or steel strip. So transfer is through the air. Now there are some other examples like say the transistors that is used in case of radios or TV or some other electronic devices, where it will reach a high temperature, say 50 degree or 60 degree or even higher. Even some of the gaming computers may reach about 95 to 10 to 100 degrees Celsius. That computer itself reach. My own computer actually it reaches about 95 to 100 degrees Celsius, and it's having a very good fan because the cooling systems will be that much efficient to bring down the temperature or maintain the temperature when it is working with the say 16 cores, 16 core processor, etc. So it's actually a high-end computer in which it requires an efficient cooling, because if you are encoding some videos or playing some games, etc., it will utilize all the processors simultaneously, and that type of processing generates more heat. So such type of computers with high-end processors or maybe 8 core or 16 core processors that requires better heat transfer methods, better fans and other stuff. Even some new computers require, say, liquid cooling systems, liquid based. Instead of air separating fan, it may use liquid based cooling systems. So anyway, such devices like electronic devices, whether it is TV or radio or computer, there are transistors or other devices which may rise up to maybe 100 degrees Celsius. That type of devices are there. Even 95 to 100 degrees Celsius is quite normal for a gaming computer. The internal temperature may reach up to that level. And it is maintained at least at that level by high efficiency separating fans. So when the fan works, you can see that the air, which is normally at 30 degrees Celsius, will flow through and carrying away the heat which is generated over the transistors and maintaining the temperature. So this is what happens in the case of a transistor, where also that, and in that case also heat exchange is there. So with all these examples that we discussed, we have come through the various modes of heat transfer like conduction, convection, and radiation. The first one is a conduction process. Another one is a convection process, and the next one is a radiation process. So, in the case of conduction process, conduction is the flow of heat in a substance due to the exchange of energy between molecules having more energy and molecules having less energy. So, here conduction is the flow of heat in a substance due to exchange of energy between molecules. So, usually there is a lattice vibrations and also motion of free electrons. So when we have a solid, then in the solid we have fixed molecules, and that solid molecules, the atoms in the solid molecules will have small vibrations. So that lattice vibrations will create the transfer of energy, or motion of free electrons also results in the transfer of energy. And for liquid or gas, it's due to the collision of molecules, moving molecules of a liquid or gas, that will also result in transfer of energy. So here the exchange is between the molecules with molecules with high energy to low energy. It's actually occurring by collision or vibration of the molecules. So that's what happens in case of conduction. Whereas in case of convection, and the main point is that the molecule actually exists on the spot itself. The collision occurs, but or vibration occurs, but it is actually not moving away, moving far away from that point. Whereas in case of a convection process, the transfer of energy from one region to another due to macroscopic motion of a fluid. The fluid can be considered as say liquid. So it's there is a flow of liquid from one location to another, and the movement of the molecules is there in convection process. And fluid added to the energy transfer by the conduction is called the heat transfer by convection. So the transfer of energy from one region to another due to macroscopic motion of a fluid added to the energy transfer by the conduction is called the heat transfer by convection. So in the case of a convection process, we have a macroscopic motion of the fluid from one location to another. The forced convection and the natural convection, two types are there. Forced convection means a fluid motion caused by an external agency. There is an external driving force, like maybe a fan or something, or some other driving force will be there, which will force the or a pump, a peristaltic pump, that will drive the liquid from one location to another. So that type of pumping or an external driving force is there for the forced convection. Whereas natural convection is the fluid motion occurs due to the density variations caused by temperature difference. For example, in a water body, in a pond or ecosystem or where sunlight falls, and even you know that the cyclone now created. Actually, there are also a process of convection where temperature differences occur in the system, and even in the water itself, the you know that the hot water will come to the top, and the cold water will move to the bottom, and that circulation actually it occurs. And this type of movement of the water molecules or other molecules will occur due to natural process, where such a density variations or heat differences or temperature differences will result in the movement of molecules, and that is known as the convection. And another one is radiation. All physical matters emits thermal radiation in the form of electromagnetic waves because of the vibrational and rotational movements of the molecules and atoms which make up the matter. So this is a radiation is by thermal or by emitting electromagnetic waves, and this radiation or thermal radiation is actually occurring in the form of electromagnetic waves, and it is because of the vibrational and rotational movements of the molecules and atoms which make up the matter. So there are two characteristics of the radiations. The rate of emission increases with the temperature, and no material medium is required for the energy to transfer. So in the case of a furnace, which we discussed earlier, there actually there is no material medium if it is not required. It is not for the transfer of electromagnetic waves, etc. There is no medium required. Because it is electromagnetic wave, the energy can be transferred from one location to another. So the rate of transfer of rate of emission increases with the temperature. So with high temperature, if your source is with a high temperature, then the rate of emission of these electromagnetic waves or thermal radiation will be high. So that is about radiation. So these are some basic concepts about the heat and mass transfer. Just now I explained what is heat transfer and what is mass transfer. So just I introduced the two terms. Heat transfer is the transfer of heat from a region of high concentration to a region of a region of high temperature to a region of low temperature. And mass transfer is a transfer of molecules like nutrients or air. Especially in case of a bioreactor, we will be discussing about the transfer of air. So usually in bioreactor, we are considering temperature control, one, and that will be where the importance of the cooling systems or cooling jackets, etc., and the overall design of the thermometer, etc., will come under the purview of this heat transfer. Whereas we have an aeration system in bioreactor, and in aeration system, we consider about the oxygen transfer, because the efficiency of the oxygen transfer in an aerated bioreactor should be well controlled or well regulated, and for which you require the basic principles of mass transfer. So the heat and mass transfer, which is actually continuously mounted and maintained, that in a bioreactor, especially in CSTR, etc., continuously stirred tank reactor, etc., that is using these two concepts. So we'll in the subsequent lectures we'll see how it is applied with heat, the further details about the heat transfer and how it is applied in the context of bioprocess. That will be discussed in the next class. Is there any questions?